Welcome to Share Science. Today we are going to explore how we commonly locate ourselves on Earth and ways we can use the stars to navigate in clear skies. It's easy to take for granted the ability for our smartphones and devices to tell us where we are on the map of the planet. But did you know you can do this yourself using the stars? Let's find out how. Today we are going to explore different ways to locate where we are on the planet. We will start with a global positioning satellite system and then look at ways we can use stars to get a pretty good estimate, which is how explorers used to before we all had smartphones. In order to do that, you will need a smartphone or other device capable of determining your GPS coordinates, a compass to determine true north, and something that can act as a sundial. This could be as simple as a wooden dowel you stick in the ground. Once we have our equipment, we are going to learn 3 key things to help answer our question of how to determine our location on Earth. 1. We will understand how the GPS system works to tell us where we are. 2. We will learn how to use the stars to get a good estimate for when our devices fail. And 3. We will know which stars we need to use depending on whether we're north or south of the equator. Here's our plan. First, we're going to determine our current GPS coordinates via a smartphone app to use as a reference. Then, we are going to locate either Polaris or Sigma Octantis on a clear night and measure its angle in the sky, which will tell us our latitude, and compare that to the latitude we determine from our GPS signal. Finally, on a sunny day, we're going to use a sundial to measure the exact time in Greenwich Mean Time that our sundial points north and use that time to calculate our longitude. We used a smartphone to determine our latitude and longitude at Share Science headquarters here in Orlando, Florida, which is 28.5 degrees north and 81.4 degrees west. The way the GPS system works is through a network of geostationary satellites that constantly beam time coordinates. Your device needs to locate at least 3 of them to calculate the time difference between the received signal and the time on the device and triangulate your position. With more than 3 satellites in view, the GPS system can even tell you your altitude. Now, sometimes we can't get such a coordinate from our smartphones. When this happens, we can turn to the sky to tell us where we are. To follow along, you're going to need a clear sky to the north and a level that can output the angle from horizontal. We use the Measure app that comes installed on iPhones, but there are others you can find on your app store. First, you need to find Polaris. There are methods you can use to manually locate Polaris, but today, since we're already using our smartphone to help us, we are going to recommend you use an app like Night Sky that uses the sensors in your phone to show you where stars are located in the sky, and we've provided a link to the app in the notes. Once you've got Polaris located, you need to open the Measure app and put it in level mode. Stretch out the arm holding your phone and point it towards Polaris while reading out the angle on your phone. You may need to try a few different orientations until you get a reading that makes sense. Here at Share Science headquarters in Orlando, Florida, we measured an angle of 29 degrees. Your number should be between 0 and 90 degrees, closer to 0 if you live near the equator, and 90 if you live in the far north. To test our measurement sensitivity, we made another measurement after traveling to London, England, which is much farther north than Florida. When we repeated our experiment, we measured an angle of 52 degrees. That's because in London, Polaris sits much higher in the sky compared to Florida. Let's think about this observation. The reason this technique works is that the star Polaris is located directly above the orbit Earth takes around the Sun. That means Polaris can always be found in the same place in the sky, regardless of where the Earth is around the Sun. Unlike other stars that track arcs in the sky through the night, Polaris stays in the same spot and we can use it to locate ourselves on the planet. By moving north or south, we change the angle that Polaris sits in the sky. At the equator, Polaris sits right at the horizon, or at 0 degrees latitude. At the North Pole, Polaris sits directly overhead, or at 90 degrees latitude. Now that we have a handle on how to determine our latitude, let's look at longitude, which is a measure of where we sit on the Earth east-west. Since the Earth spins on a north-south axis, we need to determine a starting point. At the time the lat-long system was being developed, England was a naval superpower, so they decided to define the 0 point, or prime meridian, on a point in England, namely in the borough of Greenwich in London, England, and that stuck. This is where the term Greenwich Mean Time comes from. It also means that determining our longitude in London is really easy, since by definition it's at 0 degrees longitude. We can confirm this with our method for determining longitude that uses the sun. With our sundial, we made a note of the time when the sundial crossed the north-south line that we found with our compass, and it was right at 12 p.m. noon. To figure out how to determine our longitude somewhere other than London, let's head back to Share Science headquarters and repeat the experiment there. When we repeat our sundial experiment in Orlando, Florida, we get a very different result. We keep track of Greenwich Mean Time with our phone, and we note the time in GMT when our sundial is pointing north. For us, this happened at 5:25 p.m. GMT, which sounds about right, since we know that England is in a time zone that's around 5 hours ahead of Florida. Now let's see how we can use this measurement to verify our longitude. The way we calculate longitude is by converting our time to the equivalent difference in minutes. For our location, we multiply 5.4 hours times 60 minutes to get 325 minutes. To convert this to longitude, we divide by 4 minutes per degree longitude to get 81.3 degrees. That's a pretty good estimate using a simple sundial. Now, to tell whether your longitude is west of the prime meridian or east, we use the relative time difference between your location and GMT. If you reach local noon before GMT, you're east of the prime meridian and your longitude is so many degrees east. If the GMT hits noon while the sun is still climbing, you're on a western longitude. Let's take some time to apply what we've learned. Were you able to make any measurements to confirm either your latitude or longitude? How did they compare to your actual location? The process we discussed today using Polaris assumes you live north of the equator. How would our method change if we were south of the equator? South of the equator, the Earth itself blocks our view of Polaris, but there is another star, called Sigma Octantis, that has similar orientation to the solar system, such that it's always oriented south of Earth. If you are south of the equator, you can use Sigma Octantis in the same way as Polaris in the north to determine your latitude. The process for determining your longitude stays the same either way. To summarize, we learned how smartphones are able to use the Global Positioning Satellite System to tell us where we are on Earth. We also learned if that system ever fails to work, we can use the sun and stars to get a pretty good approximation of the same information that GPS calculates, our latitude and longitude. We also learned which stars we need to find in the sky depending on whether we are north or south of the equator. We hope you liked today's video. Please like and subscribe to get more content just like this.